Well, this is the inaugural Zoom lecture. We're so fortunate to have Rachel, who is naturally au fait with computer technology. Rachel, well, before I start, I'll talk about some notices. Next month is open to the young statisticians. Emily Whitney from Curtin, who is our 2019 Honours Scholarship winner, and also Andrew Grace, who who completed a first class honours at Murdoch, will be speaking. If anyone wants to reach out to me about anything regarding the Statistics Society in this new age, I can be contacted by email anytime, and we can set up a Skype account or a Zoom account to talk. But going back, I think that's the main announcements. Rachel Cardell-Oliver is head of the Department of Computer Science and Software Engineering at UWA. Her name was put to me by last year's council as a potential speaker to our branch. At that time, she had commitments and also wondered what she could speak on. Little persuasion, she agreed to speak next year, this year in April. Rachel studies distributed sensor networks, which she was introduced to during her honours and master's degrees at computer science at UWA, and this led to a PhD on formal methods for distributed systems at the University of Cambridge. She also has worked at Essex University. I look forward to her talk, which she now presents.
Okay. Shall I go now?
Yes.
Okay, thank you very much for the introduction. It's probably a good idea for anyone who hasn't already done so, if you mute your microphones, it makes it a little bit clearer to hear the speaker. But if something drops out or my screen disappears, please let me know, because I'm still learning this Zoom stuff too. So, as was pointed out in the introduction, when I was first asked to do this, I said, well, I'm not sure the Statistics Society really want to hear from a computer scientist. So maybe I say a little bit about me, because I think that's a little bit unusual for a statistics talk. So as you've heard, I studied actually mathematics, mostly pure though, not statistics, computer science and music as an undergraduate, and then I did a PhD in formal methods. Since then, I've done a lot of work as a systems researcher. So that's somebody who builds computer systems for distributed intelligence. And I'm also a multidisciplinary researcher. So I've done a lot of work with other groups in environmental science, water, buildings, transport, and I'll talk about some of those today. So what I hope is, so I've spent most of my career collecting data, and I guess that's where I intersect with statisticians, because we're all interested in data and how we make sense of it. So what I hope is that my talk this evening, from my perspective as a computer scientist, will give some insights to provoke some dialogue about the ways that our disciplines of statistics and the discipline of computer science tackle some similar problems, but maybe from different directions. So I hope that'll be interesting. So I don't know if anybody else had this book in their childhood, but this was a book I really loved. And the reason is, from the first civilizations, humans have used measurement to understand the world around us. And for over 2 millennia, almost all of those measurements were made at a single point and at a single time. But something happened in the last century that enabled that system to change. So many breakthroughs in building, navigation, commerce, you can see many of them here, were made from measurement instruments and techniques. So the difference that I think has happened in the last 20 years or so are innovations in digital sensors, low-cost microcontrollers and radio transceivers, which has given us a completely new type of instrument for gathering distributed data at a high resolution in time and space. So my field is distributed sensor networks, and these are ad hoc self-organizing networks. They comprise tens to potentially thousands of sensing nodes. The nodes have often got short-range communication between them, so they need to cooperate to achieve anything. And the extent of these systems can be from a few meters to a few kilometers. And the temporal resolution can range from milliseconds, so partial seconds, to minutes or months in different ways. And these systems tend to be sitting in the field as a distributed network, and then gateways gather the data and relay it to permanent storage and to the internet. So sometimes, most recently, some of this sort of system have been called the Internet of Things, where the sensors are connected to the internet. So what sort of things can we do with these distributed sensor networks? Well, really, we can measure everything, and there's a huge amount of work and applications in this area. So from smart homes, you've heard, smart cities, precision agriculture is an area, natural environments I've done a lot of work in, transport, human activities, because we all carry mobile sensors with our phones, and even on or inside the human body. So there's really a lot of application areas. So what I'd like to talk about is some of the history of this area, some key research ideas, and I'd like to illustrate the development of this field over the last 20 or 30 years. So what are the main ideas? So you'll be pleased to hear that the beginning foundation was a mathematical one. So in 1976, Edgar Dijkstra, who's a professor in Holland, who was a professor in Holland, wrote a book called A Discipline of Programming. And what this did was it laid the idea of programming being a mathematical task that could be reasoned about from using mathematical techniques. And the idea was that because programs could build these, software could be used to build incredibly complex systems, we needed a disciplined and formal way of thinking about them. During the 1980s, that same approach, that idea of applying formal methods, formal techniques for understanding computing systems, was applied to distributed systems. So Tony Hoare, who's professor at Oxford, professor at Oxford, wrote a book called Communicating Sequential Processors. And Robin Milner, who again all these men have now died, was a professor at Edinburgh and was my PhD grandfather. That means he supervised my PhD supervisor. So Robin Milner wrote a book called The Calculus of Communicating Systems. And these models could be used to explore how distributed systems behave. So things like how they cooperate, how they agree, when they get stuck. So live lock is when a system keeps running, but it gets stuck in a loop, and deadlock, which is when it gets stuck completely. So that was the theoretical foundation for the topics I'm going to tell you about today. It's also an experimental science. So these pictures are all, in fact, from my experiments, looking at the behavior of distributed systems, in particular looking at the way that they can communicate. Essentially, this is the strength of the links between the distributed sensors. So experimental studies showed that the real world of sensor networks was actually, as you'd expect, much messier than the theoretical world in those formal models. So for example, communication is extremely unreliable. It varies in time. It also varies in space, and reasonably complex time series type or spatial models were needed to capture this. So what sort of things did we measure? We measured properties such as how communication varies spatially, how it varies temporally, you can see down there in the bottom. And we've learned lessons from the many sensor networks that have been built over the years. I think one of the missed opportunities is that because we haven't been very good at publishing negative results, we failed to learn from those negative results. So the experimental science actually showed up a lot of problems in the theoretical modeling, but it tended to get ignored because when people's experiments go wrong, they tend to want to put them under a bush and not talk about them. That was a pity, but in the current age of big data, I think we're coming back to the places where people can collect real data from experimental systems, and that can go into the modeling of those systems. Another huge driver for distributed sensing is commercial off-the-shelf systems. So the original systems that you can see across the top of your screen were built in university groups, and the ones across the bottom are more recent systems that are now available commercially. So many of you will have maybe an Arduino, maybe a Raspberry Pi somewhere out there in your shed to play with. And so these systems have really enabled the sorts of systems that we're now able to experiment with. Not only that, but the systems across the top, the Mica 2 and the FLEC, for example, that I used when I first started doing this research, could only be programmed by PhD students and people with computer science PhDs. They were pretty tricky to use, whereas the ones across the bottom can now be used by hobbyists. So they're commonly used in primary schools, etc. And the thing that's made that possible is good software that people can download and use and share to build these systems. So not only the hardware is advanced, the other thing that's made that possible is they've got really cheap. So the Mica 2 that I used in my first experiments was $200 or more for each of those little sensors, and Arduino's less than $10. So now it's much easier for people to build and experiment with these systems. Okay, the other thing that's changed is people. So, sorry, people haven't changed, but people are very important to consider when we build distributed systems. And I think we've seen that very much in just the last month, because people are in the loop and people and systems interact. So people were or have always been consumers of the data that's produced by sensors. But sometimes people are the producers and sometimes people are the product. And I think that's what we're seeing in some of these COVID tracking suggestions. I'll come back to this a bit later in the talk because I think it's a really interesting area at the moment. But studying people in the loop is really important, and it's not just a tech problem. It is a multidisciplinary problem where we need to think about the systems we're building, but also the psychology of what we're doing, the legal implications of what we're doing, the health and cyber policy, etc. And although it may look as if, because we've had all these advances in technology has all the answers, I'd like to caution you that we need to be very wary of what appear to be simple answers to complex problems. And I think people tracking is a particularly good example of that sort of situation. So what I'd like to do in this talk is to trace two threads of research about distributed systems. One of them, now sensor networks and distributed systems is a huge area. It's a very wide field. So what I've chosen is a personal history. It's necessary, of course, selective, and it's necessarily personal. So one of the ideas that kicked all this off was smart dust. In 1997, Chris Pista, who's a professor at MIT, came up with an idea called smart dust. In fact, he wrote a grant application for, I think it was $5 million or something. It was quite a substantial one. And the proposal was for an idea he termed smart dust. Smart dust is millimeter scale sensing and communication platforms. And this is a silly picture, but it was to show what he was thinking of. And the idea was there'd be thousands of these dust motes and one or more interrogating transceivers. Now this was, and in fact it still is, an extremely radical idea. This is actually from his grant application. He was a clever man because he presented an application scenario for the military in which dust would be scattered from an aeroplane and or a moving vehicle, and the dust motes would gather intelligence that could be used on a battlefield. So, and there were scenarios like object detection, detecting chemical attacks, mine detection, etc. So you can imagine there's a lot of military applications where this was a very promising idea. But the idea captured the imagination not only of the military who funded this initial work, but also of the research community in general. And although 25 years later, we still actually not at all near that idea of smart dust being thousands of motes being scattered from an aircraft, a lot of developments have come from that initial idea. And one of them are these whole family of tiny wireless sensors that could be programmed to work together and perform sensing. So what happened is groups all around the world started thinking about how these dust motes might communicate and cooperate. So this mote, the Mica 2, which was developed by Crossbow, they created a processor, they created radio boards, and the research group also created an operating system which was called Tiny OS. And Australia also developed a sensor which was called the FLEG mote. Now, these were actually pretty expensive. As I think I mentioned earlier, the first ones I bought were $200 each for each sensor, so hardly possible to have thousands of them. And actually they didn't work all that well. However, the initial kits made it possible for research groups to start buying the kits and experimenting with this idea of distributed systems. So here at WA, we bought some kits. So you can see here on the right, one of those CSRO flex. And on the left are some Mica 2s that we deployed down in Margaret River in a vineyard. So our first deployment was appropriately for WA in several Margaret River vineyards. And what we did is we deployed a number of motes to measure temperature and humidity in the vineyards. They collected data, but these ones didn't transmit their messages. And so we had to actually go physically down to the vineyards to collect the data from the motes. But they worked, and we got some data from them. With another set, and here's an example, I built an application for measuring soil moisture in WA soils. It was deployed, the first deployment was at Pinjar, just north of Perth. And I spent a lot of time as a hardware expert. I was in Bunnings. I built, you can see, I built boxes and joints and took apart solar lights for energy harvesting, etc. So they were the very first networks that we deployed. Some of the early work in this area was this network at Pinjar, which was measuring soil in a native Australian bushland. And that was deployed in 2004. It was actually quite an innovative project, and this paper is still being cited today because of some of the early ideas that we came. One of the features that was quite innovative is the reactivity of this system to the environment. So when the rain falls and the soil moisture is changing rapidly, the measurements were the motes collected measurements at high frequency, and when nothing interesting was happening, they went to low frequency. And so that approach allowed us to save a lot of energy by avoiding redundant transmissions. And our field trials demonstrated that it was possible to build reactive, robust, relatively long-lived systems. Okay, so now I'd like to tell you a little bit about more about the foundation. So the first one, some of you may be aware of this, but maybe not, is about shared communication. So sensor nodes in a sensor network and phones, etc., communicate using a shared wireless medium. And the problem with that is that it requires a lot of, without any coordination, it doesn't perform very well. So you can imagine if everybody is just shouting at once, then there's often interruption of the messages. So it's because when you transmit a wireless message, it's a bit like dropping a stone into a pond. The signal from the wireless spreads out. If two people independently drop stones into the pond at roughly the same time, the ripples from their stones will interfere with one another and the signal can get corrupted. And easier. So a protocol called Aloha was developed actually very early on in wireless research in the 1950s, so much earlier than this later research I'm talking about. And it's the simplest model for scheduling transport messages. And what happens is each node transmits data just whenever it's ready. And the disadvantage of that is if anything overlaps in time, then the messages will be corrupted and lost. And this lower curve is the throughput of that system. So as the attempts to send go up, the performance of this system falls away to zero. And in fact, even at best, the throughput is, it's about 18%. So it doesn't scale well to large numbers of nodes. Now, many protocols have been developed for organizing networks of nodes to share their system more efficiently. So one very simple idea is instead of sending anytime you want, there's a tick. So you can send just on the boundaries, and that gives you very much better already. That improves the throughput to nearly 40%. And then there's a number of protocols, for example, at UWA, Winnie Lewis-Lee developed something, the FlexiTP protocol, which uses timed slots and also gets the nodes to negotiate their slots for sharing. In fact, there are even protocols that make interference an advantage. So if you imagine, if you could drop the stones exactly at the same time, then their signals would actually enhance one another rather than corrupting one another. And Glossy is a protocol that takes that idea and makes the interference an advantage. So you've got constructive interference, and that can actually achieve near 100% reliability as long as the nodes are very carefully synchronized. Okay, maybe a little bit closer to the hearts of the data scientists is compression and suppression. So because the capacity, so I've just shown you that the capacity of a shared wireless channel is very low. Because of that, an intelligent approach is to send as little data as you can. So to use that scarce resource very wisely. And the way we need to do more with less. And the way we can do that dates back to Claude Shannon's work on information theory. So Shannon distinguished between the information contained in a message. So for example, if you can read this is a very compressed version, but we are able to make sense of that. We're able to extract the information that would be in the longer English sentence. And so those ideas of the difference between information and full data can also be used in sensor networks. So one of the examples of that we took in our work is a protocol that's called data-aware, resource-aware, lossless compression. So compression doesn't always mean that you lose information. It's possible to compress things without losing any information, but taking very much space. So our algorithm learns the structure of the sensor data that's reporting, and you can see some examples there on the right of different sensor time series. And then it builds a special code called a Huffman code that encodes the most common symbols using a very small number of bits, and rarer symbols are encoded with more bits. So in our experiments, we were able to reduce the size of a whole day's data to a few characters that could be sent in a single SMS message. And if you can see on the right there, the red line is our compression value, and the bottom line is actually the Shannon limit, the entropy limit. So we were able to get very close to that in a real system and using real world data. So that was a useful result. And I'd like to conclude this section about smart dust by talking a little bit about cooperation between sensor nodes. So some of you may be aware of the Argo network. It's a remarkable network of ocean floats that you can see. Each dot in this map shows you places in the world where the Argo floats are collecting data. There's 3,863 floats as of October last year. But these nodes are independent sensors. So each node submerges, it collects data by drifting for 8 to 10 days, then it surfaces again and sends its message to a base station. But the nodes don't do any cooperation between each other. So that's why it's possible to make it quite scaled, because there's lots of ocean to put them in, and they're able to send a lot of messages. However, for many applications, it's actually beneficial if the nodes do cooperate. And an example of that is some work we did monitoring round earth houses. So there were 2 round earth houses built in Kalgoorlie. And the idea of this was to look at the thermal properties of these houses to see whether they could be suitable for living in remote, arid climates. So one of the houses was built with insulation, and that's this one. You can see its behavior here on the left. And one of them was built with simply a monolithic round earth wall. And what you can see here are in the 2 graphs are the readings from the temperature sensor that were installed, actually rammed into the wall when the house was being built. So you can see how that structure is behaving. Okay, how was that an inspiration for data management? Well, I made a mistake because we deployed over 100 sensors in that house. It was funded by ARC Linkage, but we didn't put in the funding application, and I'll never make this mistake again, a software person to manage the data. And so the cost of installation of the sensors, there were nearly 100 sensors in each house, not just the temperature sensors in the walls. So the cost of installation, the cost of maintenance, the cost of managing those sensors and managing the data from them was extremely high. And unfortunately, I was the default data manager. So from that bad experience came a good inspiration. And the inspiration was this. So when we looked at all the data, we found that there was a lot of correlation, a lot of related data. And so we came up with the idea of virtual sensing and the idea of having a sense, learn, predict approach to sensing systems. So what happens in this approach is you start with a training phase, and during that training phase, temporary sensors, you can have permanent ones as well, but a large number of temporary sensors are deployed in whatever the environment is that you want to measure. After that temporary stage, then the collected data is used to train prediction functions. For this project, we actually used a pretty naive prediction function, but I'd be very interested if anyone's interested in this area to be looking at some more sophisticated ones, because we've just started some work trying to apply a similar approach to a wastewater treatment plant, and there the relation between the sensors might be rather more complicated. But in this case, we trained the prediction functions, and then after that training, what you can do is remove the temporary sensors, and so you just have a small number of permanent sensors in the building, and that makes the management of the whole system very much easier. And in fact, we found we could have reduced those 100 sensors by 60 to 80% using this technique. So that was a useful lesson for future work. Okay, so that's what I wanted to say about smart dust and where it's taken us. In the second part of the talk, and I'm not even really keeping an eye on the time, I'd like to talk about smart cities. So smart cities, I guess we've been thinking about quite a lot while we've all been locked in our bedrooms for the last few weeks. And so I think smart cities raise some interesting ideas, because so far I've talked about how to gather data efficiently and reliably. But what I'd like to talk about now is how to ensure that that data we're collecting is useful, and also some of the consequences where the data that we're collecting, and this is what happens in cities, the data we're collecting comes from people. Okay, so cities and making them better to live in have been going for a long time. So ever since people have first lived in cities, they've been looking at ways, striven to improve the ways we live in the cities. So from the Hanging Gardens of Babylon to Haussmann's elegant Parisian boulevards, to, in the 20th century, Norman Bell Geddes came up with the Futurama view of the streamlined city. It always surprises me how early this was in 1939, but the idea of the car-focused city, which now seems such a bad idea with hindsight. More recently, Shenzhen is one of the world's newest and very large city in China, with nearly 13 million people working in high-tech industries. And Perth, indeed, also striving to become a livable city. In fact, Perth has projects in sustainable cities, water-sensitive cities, livable cities, and smart cities. I rather like this one. It came from Perth Now, which don't think much of as a publication, but in March 2019, a journalist wrote, Perth has shed its title as the least livable Australian city to become the most livable. Well, except for Canberra, but who counts that? But maybe those of us that have been locked up in our local areas in this city might think, well, we've actually got a bit to be grateful for at the moment, but maybe it's not much to do with smartness. So the City of Perth and a number of Joondalup Council, a number of Perth councils have put a lot of work into becoming smarter cities. But there's another side of that, and Ben Green, who is a researcher from MIT in the US, wrote a book in 2019 called The Smart Enough City. And what he did was he started taking apart the exclusively technical view that more sensing is better and more data is better, and all we need is to collect a lot of data about our cities and all will be well. And he started taking apart some of the problems with that, particularly the injustice and inequality. He calls this the tech goggles problem. And I think in the last few weeks where we've seen some of the tracking ideas that governments are coming up with in response to COVID, that it really brings this into focus. So he wrote, before COVID, we shape technology by embedding values in its design and developing it to achieve particular outcomes. But we must be critical about the values embedded in these tools and who gets to choose them. Many technologies are designed to remedy social issues by enhancing efficiency, but that approach does not make them value neutral. So I'd like to discuss a couple of examples of how these ideas play out in practice. And the first one is water-sensitive cities. And in 2012, the CRC was launched. It had a very ambitious goal, which was it looked at transforming urban water systems from a focus on water supply and wastewater, so the taps and toilets views of water utilities, to a more complex and flexible systems. And the claim of this research endeavour was it will guide capital investments of more than 100 billion by the Australian water sector and more than 550 billion of private sector investment over the next 15 years. So I worked on one of the projects in this cooperative research centre, and I worked on smart metering. So smart metering is a sensor network technology. So we've got sensors transmitting their data by wireless for reporting, real-time measurement and reporting of household water demand. And the traditional method of meter reading, which you can see here, uses quarterly readings. They're made by a human meter reader, and the readers visit each property. So smart metering, to replace this human system, actually solves many health and safety problems that are associated with the traditional approach. However, apart from those safety benefits, the water utilities really, early adopter water utilities really didn't know what else to do with their new fine-grained data. So we looked at some of this data and at some of the things that could be done with it. And one application area is to improve operations by interpreting the water use. So what you can see here is a graph of water use per day by a single household. And what I've done is I've color-coded the different types of use. And those uses are derived by a data-driven algorithm that picks them up. So the red use here is irrigation. So you can see that it's regular amount on an irregular pattern of days. The green are leaks, so continuous flows. We could pick up peak demand. and the blue is all the rest of the background water use. So what could this be used for? Well, we thought it would be good for empowering users, because you'd know, for example, what proportion of your water use was garden irrigation, or whether there'd been a particularly bad day where you'd left the taps running all day or something, or whether you had a leak coming in. We also thought it would empower utilities, because this sort of data can be used for what's called customer segmentation, which is to identify the different types of customers and their patterns of demand. So both of those things were true, although it turned out that actually customers were not very interested in getting graphs of their data use. But the utilities were quite interested to see for the first time exactly how their customers were behaving. And one of the surprises was that in Kalgoorlie, where we did some early work, the rate of leakage, continuous flow, was actually much higher than they had expected. And on investigation, that turned out to be the water that was used by air conditioners, evaporative air conditioners. So that was quite an interesting insight. But the real impact of this work was actually in planning and delaying infrastructure upgrades. And the reason is that all of the savings, the business value of identifying types of customers or of individuals identifying how they use their water is actually not very high, whereas the value of knowing the aggregate water use and how it's distributed over time is extremely high, because when you build a water infrastructure, it's over-engineered to cope with peak use. So what we were able to do was distinguish between irregular use, so just normal inside use, and then outside use, which in Western Australia is mostly garden watering. And this graph shows you a particular region and the demand in litres per hour at different hours of the day. And the important thing about this was this peak here, because if it's possible to shift this peak, because most of its use is this discretionary irrigation use, then that would mean that the new suburbs that were being built, this data comes from Karratha, could use much less infrastructure. And so that turned out to be, I wasn't expecting it, but this, can we shift this peak, turned out actually to be the most impactful thing of the work that we did. And I think that gives you an idea of when we're, and I'm sure all the consultant statisticians in the room will know this, but the business value of the analysis we do of data is very important, although there's lots of interesting scientific things we can discover as well. Ultimately, people are collecting sensor data in order to get some business value from it. And quite recently, we've been writing up some of this work from the CRC in all the different ways that people are using the data to actually make business value in what we could call sweating the assets from the role of instrumentation, control, and automation. So I'll return to some of the reasons this doesn't happen sort of towards the end, which is not too far. Okay, so sensors. For a large class of distributed sensor networks, the sensors are people. And I wanted to talk about people because I think that's really topical while we're thinking about tracking people and contacts and where people are. So people-based sensors lead to two important considerations. The first one is that people are mobile. So far I've been talking about applications where the sensors are fixed somewhere. They're spatially distributed, but they don't move. I'm now adding the complication that the sensors move around because they're attached to people. So from your bus ticket to your phone to many types of sensors, you're moving around. And the second thing is, because they're attached to people, there's a whole lot of ethical considerations about how we use that data. So the Public Transport Research Centre, PATREC, which is a WA multidisciplinary research centre, with them, I had a number of projects analysing sensor data from your bus ticket, Smart Rider tickets. And what we've been doing is analysing and trying to make sense of how a city like Perth is growing and the way that people are using the network. So we've looked, for example, at centres of activity and the types of activity that occur there. You can see that on the left. Perth, as you can see, is still very monocentric. The size of the centre, the circles there, tells you the size of the activity. By a long way, Elizabeth Quay and Perth are the biggest activity centres in Perth. Interestingly, the third biggest is the University of Western Australia. And then, because a lot of people use public transport to get there because the parking's so terrible. Then there's a number of other centres which are growing a little bit outside the city, but not nearly as much as the main city. I've also been looking most recently, in fact, just today, at how people demand changes over time. So this is aggregated demand changing over time at a particular region. And we're also just beginning to look at how individuals change their behaviour over time. And there's some interesting problems in there. Okay, I'd like to finish with a discussion of some open research problems. So I told you about research, some of which was kicked off with the smart dust idea in the very early 2000s. At that time, there was a huge amount of hype. So there was a hype cycle. And by 2020, we've left that hype cycle. Some of the early ambitions have been realized, and there's certainly been a huge transfer of research ideas into commercial products. However, fortunately for we researchers, there's still plenty of interesting research ideas to look at, and I'd like to conclude with some of those. So the first one, which I keep coming back to, is this social license idea. So this is a talk that I first gave in October. And in October, we were concerned about the facial recognition systems that have been rolled out at the Perth Stadium, for example. So do we want face recognition running in our cities, and should people be aware that it's going on? And also early last year, or mid last year, there was a breach where the Mikey data in Melbourne was published in a hackathon for people to have a look at. And later, some privacy researchers had a look at the sort of data that could be, the sort of things that could be derived from that data. Even though the user IDs had been anonymized, it only takes 4 points in somebody's trajectories to identify a person. So there's a lot of side channels that allow privacy breaches. So that made people very nervous. It was a bit sad for me because it meant that Transperth stopped sharing their sensor data for a while we had a look at this problem. But I was very interested to see just on the 8th of April, despite this, so there was a little bit of pullback when there was a lot of public outcry about being traced, but now there's actually much more than that. So you may not know, but WA police have been given $3 million to purchase and use GPS tracking devices for electronic monitoring of people in, supposedly of people in quarantine. There's also been a huge increase of the number of cameras tracking vehicles. We have drones. Again, large amounts of money have been given to have drones which can fly over and make sure people are social distancing. Now, I understand that these are significant times and that there could indeed be some benefits from these technologies. And many people say, if you've got nothing to hide, you don't need to worry about privacy and security. But actually, I do disagree with that. And I think we need to be very careful about what's going on here. Because the privacy threats, so for having sensor data from personal trackers or number plates or whatever, are not so much the raw data that comes from those and goes, for example, to the police. But as was shown in the Mikey breach, there's an awful lot of information that can be picked up through side channels rather than directly. So something's put up with an initial reason that seems reasonable enough, but that data can be used in unintended ways and combined with data that you hadn't thought about to really be very invasive of privacy. There are also security threats like interference with the data, either intentionally or mistakenly, resulting in low quality data sets. So for example, in Singapore, I think, and Singapore are usually quite good about these sort of social systems. They're reasonably trusting about being tracked. But when the Singapore government put out an app recently to track, use Bluetooth to track contacts between people that might have COVID, in fact, very few Singaporeans, I think only 1 in 6 have downloaded the app and want to use it. As well as the tracking applications, there's also security risks with if we have a lot of systems that depend on wireless and sensor data, then they're open to being attacked in various cyber attacks. Okay, so that's one area that I think we need to be very careful of. Another area where I think there are some fascinating research problems to come. Another area where I think there are some fascinating research problems is sensing without contact or without sensors. So there's been a lot of very interesting work using background signals such as Wi-Fi, analyzing the signals from those instead of having contact sensors. And this is particularly interesting for body sensors, for example, where you could measure things as small as heartbeat or breathing from analysis of the Wi-Fi signal rather than from a body-mounted sensor. Thermal arrays are also a sensor that can be used for contactless sensing, and these have a lot of applications in, for example, sensing occupancy, how many people are in a room, so you can control air conditioning or manage emergency situations. But you'll see that unlike camera surveillance, thermal imaging is pretty good at privacy protection. And I mentioned at the beginning that communication is the communication spectrum is filling up as we get more and more wireless devices in our homes, our phones, etc. The wireless medium is getting full, basically. And so I think a really interesting area for future research is using other means for transmitting data, and visible light communication is a good one in that area. And I think this is a really cool idea, because what happens is you can transmit information by imperceptible flickering of an LED light rather than a wireless signal. And what you need is a small microchip to be included in every light bulb. And that's a huge source of transmitters, because there's 14 billion light bulbs in the world that could be harnessed for this purpose. So I think that's going to be a really interesting area in the future. And finally, low maintenance sensing. You'll see this is a subject close to my heart, partly because I've had a number of projects where I've ended up doing rather high maintenance on the systems. But there's a couple of areas where I think there's some real breakthroughs to be made. So this is a network that we've deployed on the UWA farm in Pingelly, just in the West Australian wheat belt. We're looking at a couple of ideas here. The first one is that the nodes we've deployed there are underground. So they're buried, these ones are buried about 70 centimeters under the ground, and they're measuring soil moisture. And that's really important in these sort of borderline farming areas, because the success of the crop depends on a very tiny window of when you can sow the seed and grow, because the soils are extremely water repellent. So putting the sensors underground is great. However, because the sensors are underground, the problem of changing batteries is even worse than usual. And so we want to have, well, low power. We want the batteries to last for as long as possible. But we also want to do energy harvesting there. And we're looking at technologies for harvesting energy, for example, from soil temperature differences, so that this network can really run very low maintenance. And that sort of low maintenance is key to the sorts of networks that Pista imagined 20, 30 years ago, because then the nodes really would be able to look after themselves. Okay, so thank you very much for listening. Just in summary, I've reviewed research in distributed sensor networks. I've traced 2 threads over the last 30 years. So the work on smart dust and work on smart cities. And we've seen how that vision of smart dust led to the development of low cost and easy to use hardware and software, and how I think it's been a great success, how it's enabled the distributed sensor networks to be very widely deployed and used in very many application areas. Present day visions of smart cities are built on these developments, but I think smart cities have also raised some really important issues on the complexities of these socio-technical systems and the scale of them. And also important ethical, policy and public good implications of this type of data gathering. So major achievements include understanding the real world behavior of sensor networks, designing new software, protocols and hardware to make it easy to build these systems and deploy them, and advances in data science, which help us to collect the right data and ask the right questions. And I guess that's where the computer scientists and the statisticians meet in answering those sort of questions. Thank you very much for listening.